Hello and welcome back to another video of Let's Learn Computer Science, with today's video being an introduction to computer science. Finally getting into the meat of this topic, so let's get right in. The goals of today are going to be to identify fundamental data types, variables, and operators relevant to programming. I did go to school for computer programming, so this is going to be computer science with a programming focus. And we're going to understand how computer stores the data, so let's start with that one. Computers manage data in all forms, stored as binary. Data is a raw, unrefined primary resource, and information is data that is organized to solve a problem or show trends. Something called data compression reduces the data's size. It is either lossless data compression or lossy, with an acceptable amount of loss. With the challenge of bandwidth, streaming, and networks, compression is desperately needed. There was a time when storage was very expensive. Now storage is relatively cheap. Most people have a 1 terabyte hard drive. So that was the main reason for compression. Now files are being sent over the internet. Let's talk about the difference between analog and digital data. Analog data is continuous and exact. Old radios use analog sound waves. And digital data is an approximation of analog data written in binary. So this is how infinite sound wave with infinite complexity can be represented in a finite space. So next we're going to talk about number systems. In positional notation, you read a number left to right, where left is the largest and right is the smallest. And the base of a number system is represented by the base shown in positional notation. The leftmost digit here is 9, so that's going to be the largest unit because it's multiplied by the highest power. 982 can be broken down into 900 plus 80 plus 2, where that's 9 times 100, 8 times 10, and 2 plus 1, or 9 times 10 squared, 8 times 10 to the first power, and 2 times 10 to the 0. So we can derive an equation out of this, and this is what we get. So next we're going to look at binary base 2 number system. So let's take this binary number, for instance. If we break it down and apply the formula, we can see that 1 times 2 to the 7th plus 1 times 2 to the 6th, 2 to the 5th, 2 to the 4th, all the way down. And add them all together, we get the decimal number 209. The benefit of using binary for everything is the simplicity. Binary is only ever 1 or 0, yes or no, on or off. Representing text with binary, a character set is a collection of letters and their binary representations called codes, most popular being an ASCII table, which holds 128 unique characters in 8-bit. It's 128, which 7 bits can hold. 8 bits is usually 256, but the 8th bit in a standard ASCII table is used to verify proper data transmission. It is treated as a parity bit. The extended ASCII table uses 8 bits as well, except the 8th bit is actually used to store more characters. There is no parity bit. And the most widely used one now is referred to as Unicode. It uses hexadecimal to organize its characters. The first 256 bits of the Unicode coincide with the extended ASCII table, so you don't have to change any code if you have already memorized the ASCII table. But Unicode includes every character from every language and emojis and symbols. Let's go on to the next one. Text compression is a form of data compression for text files. There are 3 main types, one being keyword encoding. It replaces commonly used words with a single character, so the word as becomes a caret, and the word that becomes a pound sign. Keyword encoding is case sensitive, so if you start a sentence with the word the, it'll have a capital T, but if you use the word the in the middle of a sentence, it'll be lowercase, and those would be 2 different things to a computer. Words like a or I do not become encoded because it doesn't save any data. Next, we're going to talk about run length encoding, sometimes called recurrence encoding. It uses flags and a count method to compress repeated characters. So here, would become the asterisk is treated as the flag, and then it's the character that's repeated, and then the number of times it is repeated. So here we have asterisk A6 denoting 6 A's, and asterisk H7 denoting 7 H's, and then an exclamation point. One thing to note about this method is that if there are only 3 letters repeated, it is not written because it takes 3 characters to encode it, so it wouldn't save on any data. Lastly, we have Huffman encoding. This is the most complex of the 3. one that you wouldn't necessarily be able to do by hand easily. Huffman encoding changes the bit string that represents frequently used characters in a particular document. A document with a lot of A's could rewrite the 8-bit string representation of A to a 2-bit string representation. Huffman realized, well, X and A and Z and E, they all have the same storage size. They all have the same footprint. But we use A's and E's way more than we use X's and Z's. So is there some way that I can make A, E, R, S, those types of very common letters to be smaller? Let's talk about audio storage. Here's an example of how audio is stored in analog form. A stereo sends voltage to a speaker and produces sound. The voltage signals vary in direct proportion to the sound wave, creating an analog representation of the sound wave. To digitize the sound wave, a computer represents the voltage as a number, and with enough samples per second, the digital version sounds good enough to the human ear. It is an approximation, and it is lossy. CDs and vinyl records both use grooves to represent sound waves, so this is a physical representation of the sound wave. CDs are digital and vinyls are analog. CDs are scanned by a laser, which grabs the binary data and sends the corresponding numeric voltage based on the binary data. MP3 files are the most commonly used given their small storage size. They achieve this by removing information that is unnoticeable to the human ear, and by using Huffman encoding. So there you go. Alright, now we're going to talk about data types. How should a computer interpret the data that is given to them, right? Because we talked about computers store all their data in binary, so it's just a bunch of ones and zeros. So how can we differentiate between the ones and zeros? So here's a list of possible data types. The first one being an integer, which holds whole numbers, signed or unsigned. Next we have a float, sometimes called a double or a decimal. It holds a rational number with decimal points. Next we have char or character. It holds a single character like a, question mark, or 1. Notice that the character representation of 1 would be different from the integer representation of 1. Next we have a string, which is a collection of characters treated as one unit of data. So this would be like a name or word. We have a boolean, which is a true or false value, a yes or no, a 1 or a 0. We have an array, which is a collection of sequential memory addresses that hold multiple values of the same type. This is how you can bundle data. And we have an object, which is an advanced data type with defined data, properties, and behavior methods. So this is another way you can bundle data, but this data, you can specify its behavior by adding methods to it. So next we have variables. Variables are a named memory location with the capability to store, read, and change the values dynamically during program execution. Variables should have a name that is appropriate for the data they represent. Most software has limitations on what a variable can be named. Variable names usually cannot include special characters. They can't begin with a number or be a reserved keyword. Next, we're going to talk about code constructs. These are 4 kind of abstract ways of defining systems of coding. So firstly, we're going to talk about input-output. Input takes information from a user and output displays information to a user. And we're going to talk about selection. Selection is executing code based on a condition, program making a decision based on information, like a if-else loop. Iteration is useful for repetitive tasks. It is the execution of the same code multiple times, or for a set amount of times. And assignment is storing a value in a variable. Move on to the last slide here. Operations. Operations are actions performed on data. Most commonly are arithmetic operations. Others include logical, relational, string, assignment, and bitwise. So here's an example in a list of all these operations. We should all be familiar with what these do. This double asterisk is raising it to the power of, it's an exponent. And this percentage sign is modulus. It calculates what the remainder of a division operation would be. Relational is also pretty self-explanatory. Greater than, less than or equal to, greater than or equal to. This exclamation point means not, so not equal to. And then this double equals just means equals to. The reason we can't use a single equals is because that's reserved for assignment, to say x equals 10. To set x equal to 10. But relational double equal sign checks if it is equal to the comparator. Next we have logical. This double and sign means and. This double pipe means or, and then this exclamation point means not. So this or that, this and not this, or not this. These are the assignment operations. I can set x equal to 10. I can add 10 to x and set it equal. I can subtract 10 from x and set it equal. I can multiply equals, I can divide equals, and I can modulus equals. And lastly, we have bitwise notation. This is an AND XOR, and this is a NOT. Bitwise is going to manipulate the data on a binary level, and then you have a right shift and a left shift to move the binary value left or right one. This concludes our introduction to computer science, and stay tuned because I'm going to have some more videos on the topic. Thank you.